Thanks everyone for coming to this edition of the Fringe Academic Festival. Together we have with us Arun Kumar from UCSD. He's an associate professor since a couple of years there. Basically, Arun has been working since the very early days, just before it was cool actually, on bringing machine learning and databases together. We have been still studying, Arun, one of your papers here at the team the last months on the normalized data and the rest of the things you have done in the past. Long story short, Arun's work has been part of commercial products, open source products. He received Sigmund Research Awards, NSF Career Award, the Rising Star Award, and a bunch of other things. So we are very happy to have him around today. He's going to talk about the DBfication of ML and AI. Arun, welcome. And just a note before Arun starts, he prefers and we prefer the questions to happen in an interactive fashion during the talk. Let's not let Arun talk to his computer for 45 minutes. So just either write something in the chat or simply raise your voice and speak out. Arun, welcome. The floor is yours.
Fantastic. Thank you, Asterios, for the kind introduction and for the invitation to the Fringe Academic Festival. It's great to be here. And as Asterios mentioned, I'm an associate professor here at UC San Diego, both in computer science and in data science, which is a new department we've had for like 4 years now. So let's dive into it. Now, it's no secret that we are now in the golden age of ML AI. As Asterios mentioned, this has been building up over the last almost a decade now. Almost all the major web companies and tech companies use ML and AI extensively for all sorts of products. And this has created enormous excitement in various enterprise sectors and other sectors, healthcare, insurance, finance, telecom, retail, and even in academic domains, virtually all the sciences and even digital humanities for tools and products that make it easier for them to integrate ML and AI into their data analytics applications. Now, here's a market code from the International Data Corporation, which studies data software space. They estimate that in the next few years, the market size is set to hit almost $900 billion US. Now, if you believe some other folks like some VCs, they estimate this in the trillions of dollars. So naturally, it's a huge pie, and a lot of people want a slice of this pie. There's several open source tools that are wildly popular. These are some of the tools that you might have used yourself. And all the major cloud vendors want a slice of this pie. They all have their own cloud ML AI services and so on. So there's a lot of action in this space. There's tons of startups as well. In spite of all this progress, as I will explain today, there still remain numerous fundamental efficiency and usability bottlenecks in the end-to-end process of building and deploying ML applications. And at the end of the day, that's what my research is about, coming up with new software abstractions, algorithms, and software systems to mitigate those sorts of bottlenecks and help democratize ML and AI-based data analytics from a data management and systems standpoint. And by democratization, I mean precisely the following: improving the system efficiency, so reducing runtimes, reducing costs of the tools involved, but also improving the human efficiency, improving the productivity of the people involved in the loop, the data scientists, the ML engineers, and so on. This really brings together these worlds of data management and ML and AI, but also straddling the whole system stack. And this is sort of what I've been doing for almost a decade, over a decade now, since my PhD days, and then subsequently as a professor here at UC San Diego since 2016, looking at various aspects of this intersection. More concretely, in my research, my style is I study and build practical and scalable data systems for ML and AI analytics. These are inspired by the principles of relational database systems that we know and love. We've been studying for almost half a century now. But I also exploit insights from statistical and computational learning theory and optimization theory, which are at the root of what ML computations are about. Now, I have interacted with almost 4 dozen data and ML professionals, data scientists, ML engineers, data analysts, business analysts, domain scientists, many people who apply ML in their application context to understand the end-to-end lifecycle of ML-based applications. And based on my conversations, I decompose this lifecycle into 3 main stages: source, build, and deploy. In the source stage, these professionals are tasked with converting raw data that sits in their data warehouses, data lakes, like multi-table relational data, text corpora, time series, multimedia data, into what we call ML-ready data sets. This is where data sets on which ML can be applied. And this involves things like collection of data, curation, cleaning, potentially labeling, transformation, and preparation. Then they apply the build phase on the ML-ready data. This is where they have to go through ML-specific tasks like feature engineering, algorithm selection, hyperparameter tuning, collectively called model selection, to build a precise prediction pipeline for their application. And then in the deploy stage, they integrate that pipeline with their application to make predictions. This could be as simple as integrating it into data systems for reporting and business analytics purposes. Could also be more complex, like integrating it to cloud-native websites or IoT applications to deliver predictions real time. And also you have to monitor the predictions, monitor the application. Typically applications evolve, the data sets evolve, so the models have to be kept fresh. So you have to iterate through this whole life cycle over time. And across this, they use data systems and ML systems implementations to execute all these phases. Now, in this context, my research approach has been the following. Based on my conversations and based on my technical understanding of the space, I abstract key steps in any of these three phases that are bottlenecks for the system and human efficiency that I talked about earlier. And based on these abstractions, we formalize the computations of what is going on, both from the data flow standpoint and from the statistical standpoint. And once we have formalized the computation, any manual work, we try to automate it as much as possible to improve human efficiency. And now that we understand the formalized computation, we can apply database and system style techniques to come up with new techniques that allow us to optimize the execution of these sorts of workloads. I've applied this in many contexts, this approach in all three contexts of the ML application lifecycle. You can take a look at my group website there for all the projects I've worked on. But for today's talk, I'm going to talk about something a little higher level, which is this general direction of what I call the new DBfication of ML AI, and then give you two concrete examples from my research in that direction across this ML lifecycle. One focused on scalable systems for deep learning workloads, and the other one is on automated data preparation in ML systems. Roughly, I would spend about 10 minutes on the first part, and probably 15 minutes on the first example and 5 minutes on the last example. But feel free to interrupt and ask questions in between. Okay, so let's talk about concerns that people worry about in ML. In the ML world, overwhelmingly, people worry about accuracy. And there's like a gazillion metrics for accuracy. There's AUROC, precision recall, BLEU score, and so on. Various ways of measuring predictions are accurate. They also worry about runtime efficiency sometimes, typically in the form of time complexity. But in the ML systems world, there's additional practical concerns that matter. What if your data set is too big to fit on your single machine memory? And increasingly in the deep learning world, your GPU memory. Scalability is a pressing concern in ML systems. And it's not enough to just be scalable. You have to also be efficient at scale. Use resources well. How are the features and models configured? ML is not just like writing a SQL query, just one-shot thing. It's a lot of iteration involved, and this is a usability concern. How do you fit these ML workflows into production systems and production workflows so that you don't have to disrupt your entire infrastructure and cause major surgeries and headaches? That is a concern of manageability. And last, how do we make it easier to build these sorts of systems that satisfy these desiderata? That is the concern of developability, making software developers who build these systems more productive. And if you look at these four concerns and think about them, we have actually been studying this for decades in the database systems world already, albeit in the context of relational and SQL computations. Now we have to study these sorts of concerns in the context of ML computations as well. And one interesting novelty that kind of makes it fun to explore this space, it's not just applying known things in the database world, because in the ML world, accuracy is very important. Sometimes you can trade off on accuracy a little bit to gain enormously on one or more of these other things. And that makes it intellectually very appealing and interesting to study this whole ML systems design and implementation space. Now, it's not just me who's talking about ML systems. There's, of course, all the big companies, like I told you, have been building these sorts of tools. This has been a push towards platformizing ML and AI. This is a famous paper from Google at NIPS 15, now NeurIPS. And here they show you the various components that go into the real world ML systems that they have. And you can see that the ML code, the algorithm that they write, the data scientist writes for the ML process. So this tiny black box inside, and then there's this enormous infrastructure surrounding this for feature extraction, resource management, serving, data collection, and so on. But this sort of platformizing of ML is not new. It did not originate in just the last few years. And here's a brief history. It really goes back to the 80s. That's when the SAS Institute started building platforms for ML computations. And in the open source realm, S as a language started. And in the late 90s, that became R, and R is still very popular among statisticians, biostatisticians, and many domain scientists. And SAS is still around. It's still widely used in many enterprise analytics space. But it's only in the late 90s and early 2000s to mid 2000s that the database systems community got involved in this space, building what we call in RDBMS ML systems. Here, the idea is data sets sit in databases, they sit in relational databases. Instead of copying and exporting and sampling the data and bringing it to tools like R or SAS, why don't we rewrite the ML algorithms as stored procedures inside the DBMS process space? IBM, Oracle, Microsoft, they all release tools called in RDBMS data mining tools for this. And they have been studied for a while. But in the late 2000s to early 2010s, people realized that to achieve that, you need to have better implementation abstractions. Otherwise, you'd be rebuilding stacks entirely for every algorithm. This is where ML systems abstractions like MATLAB came about. I've been involved with that. There were also other systems abstractions outside the RDBMS context for more scalability, like parameter server, and graph parallel machine learning, like GraphLab. And at the same time, data flow systems started taking off, MapReduce, Hadoop, and Spark. And ML libraries in that context also became very important and popular. People started doing ML on MapReduce with Mahout libraries, Spark with Spark ML, and so on. And there you had to fit your ML algorithms to their abstractions so that they run on top of those systems, similar to how you made ML algorithms run on top of DBMSs using their stored procedures, UDAs, and so user-defined aggregates. But in the last almost 6-7 years, there's been an explosion of work in this space. And by and large, tree learning systems and deep learning systems have seen enormous growth. On structured data, the most business critical workloads today use gradient boosted trees like XGBoost and LightGBM. So these sorts of systems have received a lot of attention for kind of highly scalable, efficient, easy to use kind of tools. Likewise, if you're working with unstructured data, images, text, time series, multimedia, any audio, video, deep learning is the way to go. And PyTorch and TensorFlow have grown enormously in the last few years, receiving a lot of attention across the entire system stack. And in the last half a decade or so, cloud vendors have started building cloud ML AI services, ML as a service, and they have different architectures that are cloud native and elastic and scalable. And the end-to-end lifecycle to better manage that aspect, ML platforms and feature stores have also evolved. TensorFlow Extender or TFX is one, MLflow from Databricks, and Tecton, another. These are sort of examples of these sorts of data systems for managing the end-to-end ML lifecycle. The way I see it, this sort of evolution of the rise of ML systems and platforms closely resembles the rise of relational DBMSs as data platforms for relational SQL computation circa the early 1980s. That is what I call the new DBfication of ML AI. What we did for the relational and SQL world, now we have to do for the ML world across this entire life cycle, make it more practical, more democratized. But it's not just a tool building or industrial endeavor. There's a lot of open research questions across these three phases. For example, in the source phase, you have to manage metadata for ML across feature extraction, data transformation, model training, experimentation, and so on. And that has to be done in a systematic way. You have to do data preparation and cleaning for ML, especially on tabular data that's still kind of very manual. Can we make it a little bit less manual? Multimodal ML is taking off. You have to integrate structured with image and text and so on. And so query models have to evolve. Data search systems, data labeling systems, these are all still very critical to make ML practitioners more productive, make applications more seamless. Likewise, on the build and deploy side, there's a lot of systems challenges. And we love building systems internals that are scalable. Scalable data systems for ML also matters. And just like query optimization matters in the relational context, query optimization matters in the ML systems context as well for resource efficiency at scale. And everything, analytics, workloads, a lot of them, people want to run on the cloud. You want to build systems in a cloud native manner. That brings its own challenges. Streaming infrastructure, serverless infrastructure, those sorts of challenges also we need to study. And across this lifecycle, because there's so many moving parts and components, provenance management matters. Debugging when errors happen in ML predictions. How do you fix things? Those sorts of workflows require a lot of data management challenges to be tackled as well. And once we build these sorts of tools, we need to be able to compare them on an even footing. How do you know which approach is better than the other? benchmarking, a philosophy that we know and love in the database world and also in the ML world, matters in this context too. Benchmarks to not just compare software frameworks for various metrics, but also building benchmark data sets, label data sets that allow us to measure accuracy of, say, automation of some of these tasks. And overarching concerns such as fairness, transparency, security, privacy, these sorts of issues matter in all these stages of the ML lifecycle as well, and that involve a lot of DB plus ML style concerns. So at this point, I will pause and see if there are any questions before I dive into the next part of the talk. Asterios, any questions on the chat?
Nothing on the chat, but I have a question. Actually, I wanted to challenge one of these things.
Yes.
A lot of times, when we want to optimize ML systems, all we end up doing is simply reusing known DB techniques just on the new systems. Like a lot of times. And then even if we do something fancier than what we were doing, the gains normally, especially at the data preparation side, are very small compared to the training, the time taken to train things. How do you see this? I mean, is this just a false claim? Can you give us a bit of insight?
Right. I think there is a spectrum. It really depends on how deep you look into the ML workloads. There is always the ability to kind of cast ML workloads as relational queries, right? If you just post ML algorithms on top of SQL, you actually don't have to reinvent anything. Mm-hmm. The RDBMS itself does optimization for SQL queries. And this is a philosophy that some systems do follow. Like BigQuery ML, for example, they do implement linear models on top of SQL, plain SQL. MATLAB has some of those on top of plain SQL. So that is one end of the spectrum. You don't have to do any extra work. You just need to cast the ML algorithms onto SQL. Now, that itself is non-trivial in some ML algorithm settings. You can write them as a simple SQL query, but then different ways of writing it can actually lead to different performance differences. And now all the way to the other extreme, people are actually rebuilding engines from scratch for ML systems. And so here, the idea is the compiler stack is different. The physical layer of the query execution stack is different. The data layouts are different. So even though we say it's a known technique, it's not really the same technique. You have to tailor it to the physical data workflows of these sorts of systems. Like, for example, deep learning systems, we have this notion of one of the systems we will talk about, Cerebro, multi-query optimization. How do we execute multi-query optimization on deep learning systems in a way that preserves their compilers? That is a challenge. You don't want to re-architect compilers of PyTorch or TensorFlow from scratch. They have almost 100+ operators that they support. In relational as we study, okay, 10 operators. Here you have 100+ operators from the deep learning neural computational graph workloads. So the systems building challenges change in very interesting ways. And all of this is while preserving accuracy. If you're even more ambitious, you can start studying accuracy trade-offs in the ML context in a way that understands the ML accuracy bias variance trade-off. That'll lead to even new styles of optimizations, which have no analog in the database system. So that is the farthest extreme. So it really depends on your taste and your expertise level on what sort of optimizations you want to work on, what sort of techniques you want to work on. And I think there's room for all of this.
Agreed. I don't know if you have done any research on the subject. I was wondering if multimedia databases back in the early 2000s have covered any of the things we are looking at now.
Right. So yeah, I have a colleague who's worked on that wave of late 90s, early 2000s multimedia DBMSs. Primarily, the work in multimedia DBMS is focused on inference tasks and retrieval tasks. For example, similarity search and stuff like that, and object recognition, inference, and stuff like that. So there is some prior work in the multimodal ML model space. And some of these commercial systems like Oracle, for example, you can actually store images as blobs and include functions on top of them as part of your SQL queries. But the execution engines have not evolved to keep pace with deep learning. And so one of the works that I won't talk about today, but we actually covered is a system called Vista, where we actually revisited this notion of multimodal ML for training workloads as well. And so here, this is multimodal training, where you have structured data and image data and featureized using deep CNNs. How do we make sure that you can execute that well at scale? And so that system has actually shown that there's interesting scalability challenges when you do query processing for multimodal models. Okay.
Good with me.
Any other questions?
Nothing in the chat. So.
Okay, let's continue. So now in this context, what have I worked on specifically? So I was, like I was telling Asterios, I worked quite a bit on multimodal ML query models, also on metadata management and data prep and cleaning for ML models tools. We'll talk about some of that today. I've also worked extensively on scalable data systems and query optimization for ML systems, both classical statistical ML systems and deep learning systems. And I'll talk a little bit about our work on the deep learning system space today. And I've also worked on benchmarking of software frameworks for ML and also building label data sets for some of these workloads. And in today's talk, I'll dive into two of these, one from the scalable deep learning system space, and then one a little bit on automated data preparation for ML. Okay, so let's dive into this. Deep learning. Imagine you are a data scientist, you want to train deep learning models. This is sort of the world you imagine you're going to be in. You have PyTorch or TensorFlow, awesome tools, open source tools from Facebook and Google. You specify your computational graph, you train it with stochastic gradient descent, run it on your cluster of CPUs, GPUs, maybe it's managed with Kubernetes. But the problem is this model building in deep learning is never one and done. You need to run model selection efficiently at scale. And what is model selection? This is where you have to tune your hyperparameters. Maybe you have to tune your data representation inputs, feature representation for the output, maybe the architecture itself. And so there's a lot of empirical process involved here where you train multiple models. And that process has to be handled efficiently at scale. And so in Project Cerebro, we take this holistic vision of specify the real model selection process holistically. And this is something that data scientists already know and do today. They use APIs like Keras, automated ML heuristics for hyperparameter tuning and so on to specify the larger process on top of these tools. Cerebro is a middleware system that intercepts that specification, and then it places the computations for you on the cluster. And so this is where we apply, like I was telling Asterios, multi-query optimization for deep learning systems. And this is tailored to the access patterns and the statistical properties of deep learning workloads. And we place it on the cluster in a more efficient way for executing this workload at scale. This sort of decoupling of the what of the specification from the how of the execution is also called physical data independence. This is a philosophy we know and love in the database systems world. We've done this in many systems contexts. We are bringing that philosophy to the deep learning systems context. This sort of decoupling also allows us to offer portability for these sorts of workloads. The same code stack that is sitting above can run now not only on the Kubernetes cluster, but also on cloud native execution environments. We've integrated Cerebro with Apache Spark, Greenplum, Parallel DBMS, and so on. Whereas if you were to run PyTorch TensorFlow directly on the cluster, you might have to physically specify which GPU to run what on and so on. So we published the vision in CIDR 21. Let me briefly talk about some of these multi-query optimization techniques. One of them, the first one that we published for model selection, this appeared at Sigma-DEEM in 19 and VLDB in 20. The setting, like I said, is say hyperparameter tuning or neural architecture tuning, where you train dozens, if not hundreds, of training configurations on your same training data and validate it on your validation data. And here, for example, you might use APIs like grid search, where you specify a bunch of combinations of learning rate, batch size, and so on, or random search, subset of the grids, or AutoML heuristics like hyperband, ASHA, hyperopt, and so on. Ultimately, all of these are a multi-query workload in the sense they run multiple training configurations on the same large data set in one go. This is where we now start considering multi-query optimization opportunities. So let's position Cerebro's technique versus what was happening before to understand what we are doing first. We devised a novel execution strategy for this called model hyperparallelism. So what exactly is that? In the ML world, when you have multiple models to train, this is sort of what they do. It's called task parallelism. You have a cluster of machines, you take your training data, you copy it to every machine. So that's your data set T. And then you put one config on each worker. So you put a different config on each worker. Each one runs TensorFlow or PyTorch locally, and then they train the model independently in parallel. This is really good for throughput of model selection. Now you're training a lot of configuration in parallel. You're able to get better ML accuracy sooner. This is great from the standpoint of optimization theory because your stochastic gradient descent, the optimization procedure used to train deep nets, is kept node local. And this is sequential SGD that gives you gold standard accuracy. It's very hard to beat that. However, from the data standpoint, this is very poor from a data scalability standpoint. You're literally copying a data set across workers. Now, in our use case, it's for Cerebro out on campus, we were working with public health scientists. We had a terabyte-sized data set. We're using a Kubernetes cluster on campus. If you were to use 10 machines, that terabyte size data set would bloat to 10 terabytes. And that's wastes memory, that wastes storage. If we were to store it on a remote machine and read it over the network, SGD is iterative. So now you'll be reading over the network potentially hundreds of times and flooding the network with redundant data. So on the other extreme, in the database and systems world, we know that the best way to scale to large data is data parallelism. What do we do here? You shard the data, you partition D into D1, D2, D3, and you put the shards on the individual workers. Then you have a manager or a server machine that kind of communicates updates between the workers and updates the parameters. You put one model on the whole cluster at a time, and these are highly scalable systems like parameter server. There's also Horovod, which doesn't have a server but does decentralized string all reduce across workers. All of these systems, they have high communication costs because they communicate at the level of every mini batch of data. And a mini batch of data is like a few dozen examples, maybe a few hundred examples, whereas a shard could have potentially thousands, even millions of mini batches. So you really end up communicating so many times in one pass for the data that its throughput for model selection is really low. Now you could say, why don't I communicate only once per pass over the shard? That is called model averaging. And for deep learning, that just doesn't work from an accuracy standpoint. It doesn't learn as well as communicating at every mini batch. So you end up with this dichotomous world where you either get task parallelism with high throughput for model selection, accuracy is great, but poor data scalability, or data parallelism where you have high data scalability, but poor ML accuracy behavior or low throughput. And this is where we said, why don't we get the best of both worlds? And this is the hybrid of data and task parallelism that we call model hopper parallelism. So let's see how that works. MOP is really based on a simple insight from optimization theory. Stochastic gradient descent, the algorithm to train deep learning models, doesn't really care what order you visit the training data in, as long as it is some random order. All the convergence guarantees, all theoretical results for SGD are just assume that it needs to be some randomized order. So let's shuffle, randomize the data set order, partition it across workers. You have 4 workers. Let's say you partition it across the workers, 4 shards. This is akin to your data scalable data parallel regime. But now, akin to task parallelism, we start the first epoch with different models on different workers independently in parallel. So here you see model 1 on machine 1, model 2 on machine 2, and so on. Now, these models could be different hyperparameter combinations, different architectures, whatever it is. Start the first epoch in parallel. They look at their local shard of the data. So you run the same PyTorch or TensorFlow. But at that point, after seeing the local shard, checkpoint the model, hop across workers. And so now you resume training of that model on a different shard. So notice that model 1 has hopped from one worker 2 to worker 2. And now it resumes training the same epoch, which we call sub-epoch, on the shard D2. All models keep hopping across all the workers until they see all of the data set. And that is when a single epoch has been finished by all the models. This process has strong theoretical guarantees. It is logically equivalent to sequential SGD, just like in task parallelism. Every model sees the entire data set in a sequential order, so you get best accuracy behavior. However, we also show in the paper that this approach hits the lower bound on communication cost complexity for model selection on sharded data. So you cannot do better than this on the communication cost compared to, say, the task or the data parallel approach when you have sharded data and you need to train a lot of these models. Now, this approach sounds simple enough. In this paper, VLDB 20, we actually go into the implementation of these systems, some of the systems issues involved. In general, Cerebro involves a resource-aware scheduler, and you can cast this as an instance of the OpenShop scheduling problem. You don't have to have every model wait on each other. The models can hop across each other without any synchronization points. We call this bulk asynchronous parallelism. This is the first known variant of bulk asynchronous parallelism, kind of what we know in the database world as bulk synchronous parallelism. And so we could support this for evolving configurations like AutoML heuristics. They add configs, they delete configs over time. Those sorts of things can be naturally supported on this. And we also can support data replication, fault tolerance, elasticity. If you want to add shards to new machines, you want to add new machines and so on. All of that works easily with MOP. And we showed that you can get all of this without needing to do major surgery to deep learning systems. TensorFlow, PyTorch, these sorts of tools already offer APIs for checkpointing model and resuming training. We don't need to change anything in their internals. Cerebro can integrate as a layer on top of these sorts of tools directly. So does this actually work well? We took a benchmark workload, ImageNet. This is from the computer vision world. And this, we trained 16 state-of-the-art CNNs, ResNet model, Inception models, standard off-the-shelf architecture from published vision papers, 8 different hyperparameter configurations for each, implemented in TensorFlow on an 8 GPU cluster. So this is on campus. And so here, I'm going to show 2 things. This is a snapshot of the key results from the paper. There's more in the paper. You have the epoch on the x-axis and the benchmark accuracy metric, the top 5 validation error on the y-axis. This is called the learning curve. We have these 5 systems we are comparing. We're comparing Cerebro against Horovod, which is the state-of-the-art data parallel training system, Celery, which is a task parallel training system, model averaging in TensorFlow, which communicates updates at once per shard, and parameter server asynchronous, which is available directly in TensorFlow, also a data parallel system. Model averaging does not converge well. Horovod converges better. So notice that accuracy needs to improve over the epochs. Lower is better. Parameter server asynchronous also works well. Horovod and parameter server asynchronous have slight gap, but that gap can be mitigated with Horovod's Beanie batch size adjusted. Celery, Cerebro, and parameter server, they all have similar accuracy, similar kind of learning behavior. Notice that Cerebro is virtually indistinguishable from the task parallel tool Celery. However, if you look at system metrics, these are the runtime numbers and the memory and storage footprints. Parameter server is super slow. Horovod is almost 3 times slower than Cerebro. Model averaging doesn't convert, so we don't really want to use it. Celery and Cerebro, they have similar runtimes, but Celery has almost 8 times the memory footprint of Cerebro because it replicates the full data across the machines. Overall, if you take resource metrics and ML accuracy and learning metrics together, Cerebro offers the best combination of resource efficiency and accuracy. And this is achieved really by understanding the data access patterns of these workloads, bringing together the database system style approach of synchronous parallelism, modifying it to asynchronous parallelism for multi-model execution. Now, there's more experiments in the paper with other data sets, other model selection workloads, AutoML heuristics like Asha. We've also compared this with other backends like remote reads, what is the network cost, and so on. So I'll invite you to take a look at the paper as well. Okay, I'll pause here and take more questions if any. No questions on the chat?
Nothing in the chat.
Okay, so then I guess I can continue.
Yes, please. Nilay has one. So yeah, let's
go for it.
Give it 3 seconds.
Can you read the question, Asterios?
Yes, when I think Nilay is typing.
Okay.
Or Nilay, you can simply open your mic.
Yeah, hi. Thank you, Professor, for the opportunity.
Yes.
So I was also quite curious that would it generalize well with every kind of model we were working on? Because this, I think it's ImageNet is definitely of one specific domain.
Right.
And
okay. So the question is
that in a different domain we'll see different results.
Right. So the question is, will it generalize to any sorts of models that we work on? The answer is yes, because if you look at exactly the approach, all it does is it places the architecture on the machine and runs local PyTorch or local TensorFlow on that machine. It's orchestrating the work across machines. So within the local machine, we don't modify anything in PyTorch or TensorFlow. What that means is literally any architecture that can be specified in PyTorch or TensorFlow will work out of the box in this system's context. So transformers, time series models, and so on. For our public health use case, we actually applied this for CNN and LSTM hybrids, time series models for large scale training. We've also tested this on BERT style models and transformer models as well.
Okay.
The only one it won't work on is graph neural nets. Graph neural nets do not have the sequential access pattern for SG. We have a separate system for graph neural nets in the works. Look out for that later this year.
Yep. Makes sense.
Okay.
Yeah. And we have another question by Andra. Andra, go ahead.
Hello. In terms of performance, you said that Celery and Cerebro are more or less the same, except of the memory footprint.
Mm-hmm.
If we disregard this, what's the overhead of using Cerebro versus using Celery for the same thing?
Right. Thanks for the question. So the question is, what's the overhead of Celery versus Cerebro? What's the overhead of Cerebro if we disregard memory or storage footprint? The answer is really the communication that you do for the model hops adds a little bit of communication cost. But what we found in the paper, we actually have the detailed Gantt charts that is actually inconsequential in the overall runtimes. The model hops across the machines account for less than 1% of the overall runtime. However, if your models are extremely large, you're operating in the very large model, very large data regime, then the communication costs across models will go up. But because you have a very large model, the computation cost on the workers will also go up proportionally. So we expect that number to not change much. That said, if you're able to afford infinite storage, infinite memory, and you don't mind reading it over the network or something like that for remote reads, then possibly the overhead of Cerebro would be in the orchestration. You have this scheduler kind of handling these different things. It's basically an additional piece of software that you need to run instead of just doing regular task parallelism. Does that answer your question?
Yes, thank you.
Okay.
Got
Now,
it?
one of the things is we have a similar idea for model scaling. We talked about models being large. If your models are large, typically people shard the models. And we have an analog of model hopper parallelism for large-scale model training as well. I'm happy to chat more about that if you're interested later. Okay.
Got it? Arun, we have one more, if you don't mind.
Yes, let's go for it.
Yes.
Yeah. So you brought up this idea of the models hopping across these machines, and this might be coming from a small space of ignorance in this term because I haven't done a whole lot in terms of parallel work. So in what form are those models moving from machine to machine? Is it just the saved weights, or is it actually the full like binary of the model that's moving across? And is it possible to reduce that overhead you were just talking about if you change the form in which you're sending those models across the machines?
Right. So this is an implementation decision. For simplicity's sake, we just use the saved model format that the TensorFlow offers, or PyTorch pickled models. Like you just save the model binary when you checkpoint it, and then you resume from their format. So really, we outsource that decision to the deep learning tool. Whatever format they prefer writing it to, they would just resume. So you only need the information about the parameters that are there, and if needed, any optimizer state. Like if you're using ADAM or some adaptive gradient algorithms, you have some extra state information. It's very minuscule information. That's all that we are saving. And now, for the purposes of Cerebro's implementation, we just write it to a network file system. So it's a shared file system, and then you read it from the other worker. That turns out to be very simple to implement. You don't need a complicated direct machine-to-machine communication infrastructure, because that's an overkill. And I think simplicity is something that I really love in system design, as long as it satisfies all our metrics. So that's sort of what we do. Now, from the standpoint of optimizing it, the question is it worthwhile? Because it's not dominating the runtime, it's only 1% of the runtime. We didn't bother optimizing it. But in the future, if that is the case, then you can potentially think of things like compressed, saver, and kind of more efficient communication infrastructure. Okay.
Thanks.
Cool. Great.
Let's do this. Yeah.
Let's continue. Thank you for the questions. So now that is the model hopper parallelism. The whole vision of Cerebro involves orchestrating model building for deep learning workloads at scale across multiple sorts of model building tasks. Hyperparameter tuning, architecture tuning. There's also transfer learning and feature transfer that we have studied. Machine learning over groups, where you train different models for different subsets of the data. Akin to the group by clause in SQL, you can do group by for machine learning. Sequence analysis, graph analysis, like I said, we've been studying this for the last 5-6 years. And in the CIDR paper that appeared 21, we've laid out this whole vision. It's a layered stack. You have the model building APIs on top, using exactly the same interfaces and tools that data scientists love. At the bottom, you have the execution layer and the storage layer. Cerebro can work with multiple backends, direct file system access, Kubernetes clusters like Dask, or even Ray. We've integrated already with data flow engines like Spark and Greenplum, and we're also building a cloud-native execution engine on AWS. The secret sauce is really in the middle, which is the optimization and scheduling layer. This is where we bring in these multi-query optimization techniques based on our understanding of the workload's access patterns and statistical properties. And the underlying execution engine's properties, we kind of rewrite the what of the execution into the optimized how of the execution. This is where model hopper parallelism and various hybrids of it for model scaling, for group learning, for graph analytics and stuff like that are being executed. For transfer learning, we also have data materialization management that's involved here. And all of this is wrapped around TensorFlow and PyTorch, which is what we use for automatic differentiation and SGD execution. So we don't have to change anything in their internal code. Now, all these models that are being trained, you need to manage the metadata. You need to have kind of visualization capabilities. All of that is orthogonal to what we're doing in Cerebro. So we just integrated with regular tools like MLflow and TensorBoard. You could build a graphical user interface as well. You can visualize this sort of process there. And all of this will happen in a fault-tolerant and elastic manner, especially on the cloud. So to summarize, Cerebro is this model selection first layer data platform for scalable deep learning. It combines higher level specifications, which data scientists already know, with multi-query optimization techniques inspired by what we've seen for the relational context, but adapted to the deep learning training context, allows you to get better resource efficiency and improve user productivity, where they are focused on the ML goals rather than kind of systems, metrics, and scaling. Now, Cerebro has been used so far by public health scientists, like I said here at UCSD, on terabytes of accelerometer data. We've published 4 public health journals based on this. The models built with Cerebro are the state of the art in their field now. Other data, domain scientists are using it across the US and Australia and so on. We're also collaborating with computational physicists to apply some of these techniques in their context for fluid dynamic simulations. MadLib, part of Apache project, for a pivotal that was acquired by VMware, shipped model hopper parallelism on top of the Greenplum DBMS. It's open source. And Cerebro, we've integrated with Spark, that is also open source. We're now making more of this technology available for different workloads, including for model scaling, and we're integrating it with the San Diego Supercomputer Center's infrastructure so that more domain scientists on campus can access these sorts of benefits. I'd like to thank all these agencies for funding this project. So you can see diverse mix of groups from public health to the basic science to industry as well. So this is an interesting, exciting space to bring together these worlds of systems, databases, and machine learning. So that was the first example. I hope that kind of showed you what I mean by this new DBfication. We are re-architecting and reimagining the platforms for deep learning world inspired by what we did for the relational world. Now let's transition to something very different, which is data preparation. And this one I will talk more briefly about. In the context of machine learning on especially tabular data, data preparation matters a lot. How you transform the variables, how you prepare and clean the features and stuff. Now, there's been a flurry of work on what are called automated ML or AutoML tools. Examples include Salesforce Einstein, SageMaker Autopilot. These sorts of tools automate your hyperparameter tuning, architecture selection, and stuff, feature engineering. But in the last few years, they started claiming they automate data preparation as well. And this is a chart from Salesforce Einstein's Transmogrify, which is like a tool they open source. They call transmogrification as data preparation. Autopilot also claims it automatically transforms data. And then TFX, we collaborated with the TFX team at Google also. They have Auto TFX where they also want to do transformations automatically. So they claim they have automated data prep. You just give a tabular data file, it'll build a model end-to-end for you. But then I looked at this and I wondered, just how good is their automated data prep, objectively speaking? Turns out that no one knew. And for ML aspects like hyperparameter tuning, feature selection, people knew. Data mining folks have studied that for more than 20 years, but not for data prep. So this is where we set about creating benchmarks for ML data prep. And in Project Sorting Hat, we laid out this vision for what should benchmarks look like. And we find there's 3 components that are necessary. One, you need to formalize the task definition. What is the input? What is the output for a data prep step in the ML context? 2, we need labeled data sets, input-output pairs, to assess the accuracy of an automated data prep method. And 3, it's not enough to just automate it. We want to make sure that the way you automate it doesn't affect your downstream accuracy too much, or it actually improves it. So you need a benchmark for the downstream predictions as well for whatever data prep automation you've done. Does it really help? And it turns out that this led to a big open question in the space at the intersection of databases and ML theory. How does data prep actually affect ML accuracy is a big open question that people don't really understand. In the database world, they've studied data preparation and cleaning for SQL analytics, for business intelligence, for knowledge-based construction, and other sorts of applications, not for ML applications. How you do data prep in the ML workflow affects your bias variance noise trade-off. And the way you affect it can be nuanced. And so understanding this in depth can not only reveal the close interaction between data prep and ML accuracy, but it can also lead to interesting new what we call fail-safes for these end-to-end AutoML tools. Like if they know that the error is going to fall this way or that way, they can execute alternative execution paths and build fail-safes to prevent those sorts of downstream failures. So this is sort of a new greenfield space. We started studying this with some of these tasks that we consider as crucial. And so we did a survey of all the open source industrial AutoML tools that do automated data prep, spoke with practitioners, and then identified a set of common tasks. These are by no means exhaustive. Data prep is very large. There's probably dozens, if not hundreds of tasks. These are some common tasks that we saw that are important. And we cataloged them in this benchmark called ML Data Prep Zoo. And here, for example, task 0, you upload a database file, which is a CSV file. Maybe it has a bunch of features about, say, customers for churn prediction. Age is stored as an integer. Income is a string. Zip code is an integer. The first thing you have to do is called schema inference or feature type inference. For example, zip code is not an integer for machine learning. If you give that as an integer for machine learning, it'll give you garbage results because you cannot add or subtract things there. You have to cast it as a categorical feature, it's a discrete set. So we come up with this issue of identifying the feature types, bridging the gap between what ML model wants and what databases schemas store. And likewise, there's several other tasks, category duplication, embedded number extraction, and so on that we listed. Let me dive a little bit into the schema inference tasks. We've actually published a Sigma paper about this. We created the first benchmark for this task of feature type inference. How do you detect what features are present in the tabular data file for ML? We classed it as a multi-class classification problem. Basically, 4 things that we did. We standardized the label vocabulary based on unifying things from TFDB, AutoGluon, Transmogrify, and many of these other open source tools to identify these are the categories of discrete labels: numeric, categorical, timestamp, string, and so on. And once we did that, we kind of create a mechanism to featureize the raw column data to identify the feature type. And we created large label data set, the first large label data sets for this task. This is based on almost 700 files we downloaded from Kaggle, UC repository, and several other public sources, and we manually annotated them with ground truth labels. And we then trained ML classifiers based on this, standard cross-validation methods, standard classifiers with standard featurization methods, like random forests and nearest neighbors, CNNs. And these are the key results. And the details are in the paper. There's a lot of experiments in the paper. The highlight results is that even standard ML methods like random forest, based on standard text features, boost accuracy of feature type inference substantively compared to what TFDB did, TensorFlow data validation, or AutoGluon did, or Transmogrify does, by even 15% on the lift. And this is for a binarized version of this classification test where you predict numeric versus categorical. This is really because of the semantic gap that is present. What is stored as an integer is not necessarily an integer for machine learning. And we benchmarked also on downstream data. We tabulated over a dozen downstream data sets, and we find that not doing this data prep step accurately can significantly affect your downstream accuracy. And so based on these results, as you can imagine, some of these companies got really interested. Google and Amazon, they gave me some gifts to collaborate with us and kind of adopt some of these methods into their tools. TensorFlow extended team will work with us for a couple of years. We integrated one of the models. We built the random forest model for type inference into TensorFlow data validation. They're benchmarking on their internal AutoML benchmarks. Amazon, the AutoGluon tool, also kind of wanted to adopt some of this. Redshift ML folks work with us as well. OpenML, which is this open source ML data science repository, Joaquin's group, they're doing terrific stuff. They also wanted to kind of use some of these random forest models for type inference to make it more automated for their platform. We're also using this tool for model dataset search called AI Maker. It's an NSF-funded project with a colleague here, and these models for type inference are also used in that context. So just
Arun,
one
quick question on this one.
has these applications. Yes, question.
Quick question, Asterios here. How does this? I mean, I see that the first part of this pipeline is very similar to what we call semantic data type detection.
Right.
So basically, on top of semantic data type detection, you have listed some specific data types to
Correct.
be either categorical
Correct.
or numeric. Okay.
Yeah, so there is a dichotomy here. This is feature type for ML. Semantic type is typically for the BI context for human consumption. What we found was all 4 combinations are possible. A semantic type can be categorical or can be numeric for ML. And likewise, a categorical feature can be different semantic types or different numeric feature can be different semantics.
Yes.
So there's also combination. So it's really a complementary task. That's sort of what we found. In the paper, in the Sigma paper, we actually go into one of the latest semantic inference models that people have open source. It's a machine learning model. And we kind of layered a rule engine on top to categorize into ML feature types. And we found that actually doesn't automatically capture things. You still need to do some learning on top for ML feature type.
Cool. Nice.
Okay.
Yes.
Was there more questions?
None that I see here. We have one. Got it.
Yes. Go for it.
Yes. Hi. Sorry, I was getting my microphone figured out there. So in terms of your process of creating those categories of your data, if I understood your explanation of it correctly, it's based on existing data sets and everything, and then you create this standardized label vocabulary. You consider gender as a categorical. Does it deal with I'm trying to think of how to phrase this question. Does it allow for more than just binary values when you featureize that raw data, or is it?
Absolutely. So
Okay.
because it's categorical, it's a discrete set. That's all it means. You could have many categories for gender, right? So
Awesome.
Now, from the standpoint of the vocabulary, how we got the label vocabularies, the details are in the paper. We actually surveyed some of these industrial open source tools. What are the vocabularies they use? And then we created a superset. And we actually show a mapping from what they do to what our vocabulary is. We have a 9-class vocabulary. And these are very standard intuitive things like numeric, categorical, timestamp, string, and so on. There's also one for other types. If you have rich, like nested data types and stuff, somebody has to sit and intervene and cast it as basic types. And in the paper, we actually show the distribution of from our benchmark label data, how many belong in each of these categories, how many columns exist in the numeric type, in the categorical type. It turns out that almost 80% of features that exist in tabular data are either numeric or categorical. Okay.
Awesome. Thank you.
Yes. We have one more question. Ziggy?
Yes.
Yes. Hi, Arun. I'm having a question regarding, do you also consider data prep for unstructured data? Because usually, for example, some state-of-art models, they will train on some specific data, for example, COCO or ImageNet. So usually these models, it seems few of them are researching on how you should prepare data for better models. So have you ever think about this?
That's a good point. So we haven't considered unstructured data in this context, mainly because the data prep aspects for unstructured data are not as complicated as for tabular data. Especially in the deep learning context, you probably don't need too much data prep nowadays. Raw data, featureization that happens in the model suffices for many text tasks or time series tasks. But it's an open question. Are there things that lead to a semantic gap in the way data preparation works for those sorts of data sets? That's an interesting question to study. Certainly on the tabular data context, there's a big gap. And so that's why we dove into kind of this particular aspect, because we thought that was the most interesting aspect for us to study.
Yeah, thank you.
Okay. Now, even in the tabular context, you would notice that there is strings sometimes, like text, review text. So even though I say it's tabular, it's sometimes multimodal. And so data preparation on tabular, you'd have to integrate that with some of this stuff. And so as we go down the hierarchy of data prep tasks, at some point you will encounter text processing as well, at the least. Okay.
Can I ask a meta question, Arun?
Yes, go for it.
I'm very interested. How easy or hard was it to publish a benchmark paper?
Very hard. So the vision paper we published at DEAM was very good. DEAM was a very welcoming environment for end-to-end data management for machine learning. So kudos to Sebastian, who's also at Amsterdam, right? He started this and I helped him with this. And yeah, DEAM is a very nice environment. Publishing it at Sigma, VLDB, MLSys has been hard because these communities, they didn't value benchmarks as much for data sets and so on. Turns out that alongside our work, VLDB itself was evolving. So in 22, I was involved with the scalable data science track, but they also expanded their experiments, analysis, and benchmark category in the research track to also include benchmark data sets. And so literally alongside what we were doing in this work, people started realizing that label data sets are important, benchmark tasks are important. VLDB evolved, NeurIPS also evolved. They launched a new benchmarks track in NeurIPS just a couple of years ago. So both the database and the ML worlds now value benchmark data sets. So I hope that continues.
Yeah, me too. It is amazing how bad we are in publishing and respecting benchmarks.
Absolutely.
Sometimes I find it unbelievable. Anyway, okay. Thank you.
Okay, sounds good. So that's about it. I think we're at the top of the hour. I've kind of hopefully I've shown to you that this is the new DBfication of ML AI presents exciting research challenges across the entire lifecycle. I showed you stuff from data prep for tabular data to systems for large-scale deep learning. And I didn't talk about probably 80% of the work we've done. So there is a lot more work that the entire community needs to step up and do. It's not possible for one person to study all of this, of course. So leaving these sorts of problems open will result in a huge waste of time and effort for these data and ML practitioners, money for these organizations, and energy, especially in the deep learning context, by all sorts of users of ML AI, domain sciences, enterprises, web companies, and so on. So it's really a shirking of our intellectual responsibility if we don't address these sorts of issues. And it's high time for folks in the database community, ML and AI communities, and all of these communities to join forces to accelerate this DBfication of ML AI to help democratize ML AI. And I hope we can continue to work with ML users and AI users in the domain sciences if you're in academia, in industry, potentially with collaborations like some of the collaborations I talked about. And I hope this sort of interactions continue and we continue to accelerate this DBfication of ML AI. So, and I was just mentioning publication menus. I was involved with the scalable data science track at VLDB, helped launch and run it for 2 years. Sigmod also has something like this. MLSys is a new conference for ML systems. KDD has something like applied data science as well. So there are new publication avenues as well. If you're doing this sort of work, if not the regular research track, these sorts of research track aim to encourage work of this sort. So all these communities are now seized that this matter is very important for the future of computing itself. And so hopefully the community continues to support and evolve in this front. So with that, I'll stop. These are my terrific student advisors who've been working on all this stuff. Supun led some of the work on Cerebro, Juha and Kabir as well. Raj led some of the work on Sorting Hat. He actually wrote grant proposals for Amazon and Google that got funded. So spectacular. So I'd like to thank all these students. And with that, I'll stop. All the papers, code, data, models, blog posts, videos, talk slides, everything's available on our lab webpage. Go to the respective projects there. Feel free to shoot me an email if you have more questions or follow me on Twitter if you want more frequent updates. With that, I'll stop and I'll thank all these agencies that funded our research. Thank you again to the audience for joining.
Excellent. Thank you, Arun. Do we have questions? I would spare a couple of minutes.
I have a question.
Yes, go for it. Yes, I can. Go ahead.
So, Arun, as you said, actually you have much more DBML work, which you didn't introduce today. I hope to ask at a high level, what's your opinion that how shall we use the database technology for machine learning and deep learning? For example, I'm more familiar with your work about factorized learning. Right. There, basically, why factorized can save time and storage is because this kind of redundancy residing in databases because of like functional dependencies. So what's your opinion on this? Because when I saw Dan's work, it's similar, but they are using aggregation and ordering. So what's your insight all these years working on these topics?
Right. So the question is on factorized learning and how the DBMS itself can be useful in this context. So
also in general.
In general, yeah. So in the factorized ML context in particular, I've studied it in the DBMS context, in the data flow systems context as well, and also in the in-memory context, like R and Python workloads, like in the project Morpheus. So we've actually shown that factorized learning can be beneficial for in-memory analytics, for in DBMS, and for on data flow systems. So the way I would approach this is using the DBMS artifact in the ML workflow is one direction, but also bringing DB style techniques to ML systems is a different direction. I think both of them can be valuable. DBMS in the context of the ML workflow, the amount of computations that take place there compared to the outside DBMS is probably not that high anymore because you have all this evolution of all these other systems. However, that doesn't mean that in DBMS ML is no longer existing. All the cloud vendors, they run in DBMS ML now, Redshift ML, BigQuery ML, and so on. So there is some scope there, there is some value there. In the deep learning context, for example, a couple of years ago, we published a paper along with the MADLib folks. How do you do in DBMS deep learning? So this is the integration of MOP with GPDB, Apache MADLib. MADLib is an in DBMS ML library. So that is sort of the state of the art, how you can run TensorFlow from the DBMS process space. You have a SQL query where you want to invoke training or inference, But the model architecture and the compilation happens in TensorFlow process space. DBMS handles the tuples to the TensorFlow process from a user-defined function. So there is an interesting paper there that you can take a look at that as well. I think there is some scope there as well. Now, in terms of factorized ML in particular, I mean, I did attend Dan's workshop. He had a workshop last year about factorized things at Zurich. I didn't go in person, but I attended virtually. And one of the things is factorized ML really matters in the context of ML computations that sit directly on the data. But if the ML computations that are not directly touching the data dominate your runtime, factorized ML won't give you as much benefits. And so in the deep learning context, it's only the first layer that touches the data. So, and people don't use deep learning methods on tabular data that much. They use tree boosted methods. So really understanding factorized ML in the context of tree boosted methods is an open question. So there's still some interesting work to be done there. I have since evolved after kind of joining as a faculty member. I moved away from that topic a little bit because I wanted to explore some of these other topics, but I think there is still some scope for stuff to be studied there. Now, this feature store stuff that I'm talking about, like people are trying to commoditize feature workflows. Factorized ML can matter in that context. You can integrate, for example, learning over the base tables rather than a materialized view. That can be an optimization in feature stores that can be potentially helpful because they actually maintain those sorts of materialized views. That's their job. So that's something I would encourage you to take a look at as well. Okay.
Okay.
Great. More questions?
Great. Now,
no?
In the absence of other questions, and especially time, we would like to thank Arun again. Arun, thanks for taking the time and being with us. We hope to see you soon in a physical conference.
Absolutely. Thank you again for having me over for this. And thank you, Asturias and Lorenzo. And thank you to the audience for joining in for all the excellent questions. Take care, everyone. Yeah.
See ya.